This video is not necessary for the course. You will not be tested on this. This is just if you really want to understand how the radical thing works and you want to understand it on a deeper conceptual level, and maybe you want to become a math major or an engineering major or some cool thing like that. Anyway, let's start with our most basic example of a radical or a root or whatever, the square root. The square root of a is the number x such that the square of x is equal to a. Or simply put, if x squared equals a, then the square root of a equals x. All these variables might throw you off, but it's really simple if you just substitute some numbers in them. So x squared, well, what if we said 2 squared? What do we know that 2 squared is equal to? 4. Hence, we have that the square root of 4 is equal to 2. This fits our basic standard definition of square roots. And even 3 squared, we know that's equal to 9. So the square root of 9 is equal to, you guessed it, 3. And we can move on to our next definition. The cube root of a is the number x, such that x to the third equals a, and we get that the cube root of a equals x. Very simply put, we know that 2 to the third is equal to 8. Then we know that the cube root of 8 is equal to 2. Pretty simple, right? And we can even go a little bit further. 3 to the third is equal to 27. Hence, we get that the cube root of 27 is equal to 3. Now, because we are going to learn this on a deeper level and understand the whole conceptual framework of these roots and stuff, we have to generalize. And generalize means no more numbers. So we're going to define the nth root of a is the number x such that x to the n is equal to a. And from there, we get that the nth root of a is equal to x. All that we have done is, instead of defining things number by number, instead of saying that the fourth root of a number is a number x such that x to the fourth is equal to, we're just replacing 4 or 3 or 2 or whatever with n. N can be any number. It can be -1, -2, it can be a million. And we're always going to have the same rules work. This is what we mean by generalize. We're going to show that some of these basic properties of radicals / roots apply in any type of situation, no matter what the root of that number. So, easy way to understand this is, let's prove some basic facts. Well, what can we prove? Let's start out simple. Let's prove that the nth root of two numbers a times b is going to be equal to, what is all this nonsense? The nth root of a times the nth root of b. Well, if we follow our basic definition of the nth root of a number, we know the following. We know that if we were to take this whole thing here, I'll even write it out, nth root of a times b, and we were to raise that to the nth power, what would that be equal to? Well, by our definition, it has to be equal to a b. This makes sense, right? We know that it's all just following our definition. So if this is following our definition, we need to, and we're trying to prove that all this over here is true, all this is true, then we must also show that the nth root of a times the nth root of b raised to the n is going to be equal to a times b. This is what we want to prove or want to show. Because then if we show that these are both equal to AB, then that proves our original theorem that the nth root of AB is equal to the nth root of A times the nth root of B. So let's just clear some of this off and we'll get started. So let's take, again, we're working with these two right here. We're going to be working with this. And let's just say that x, some number x, is equal to the nth root of a. Because the nth root of a doesn't, you can pick any, you can pick, what was one of our examples? The cube root of 27, right? Well, that has to be equal to some number. It's going to be equal to 3, right? Instead of writing 27 where a is and 3 where the n is, and saying it's equal to 3, we're just assuming that if we take the nth root of some number a, it has to be equal to some other number. And we can say the same thing about the nth root of b. So I'm going to say that y is whatever the nth root of b is equal to. Because again, the nth root of b has to be equal to some number. So then if we replace what we have here, instead we're just going to have x times y. Again, that just follows from our two, you could say, declarations that x is the number that the nth root of a is equal to and y is the number that the nth root of b is equal to. So now let's take this value and raise that to the nth power. And if we raise x and y to the nth power, well, we know the rules for exponents and how that works. We just distribute the nth power to both of the terms. So we have x to the n times y to the n. And again, if you're not familiar with this, it's okay, but it basically comes from what you hopefully learned in Algebra 1 about when you raise, when you put a power of a number outside the parentheses. So now, if we go back and substitute in our original value for x, we are going to get that we have the nth root of a raised to the nth power. That's our x value. And I'll even write the y part in blue times, and now we're going to get our y part, substitute that back in, times the nth root of b raised to the n power. It should be clear to you what's going to happen next. Well, the nth root raised to the nth power is just going to get you a. And the nth root of b raised to the n power is just going to get you b. And since we got that, then we absolutely know that our original, I'll try to write it in a different color. I know it's getting a little cramped, but we know that this statement must be equal to this statement because we already showed earlier that the nth root of a times b, if you raise that to the nth power, well, that also equals a times b. So since this is equal to this, we just proved it true. We proved that since they're both equal to the same thing, they must be equal to each other. Well, what does that tell us? All this proof tells us is something like the square root of 6, which is equal to the square root of 2 times 3, is also equal to the square root of 2 times the square root of 3. That's basically what we just proved. Very simple proof, and with very cool consequences. And also we'll know that, you know, this works for any root. So if I have 4 and 18, well, I know 18 is the same thing as 2 times 9. So I would also know that this is the 4th root of 2 times the 4th root of 9. That's a consequence of the proof that we just did up here. So now let's clear our page and see if we can figure out anything else. Well, what else can we figure out? Well, we now know, because we just proved it, that the nth root of AB is equal to the nth root of A times the nth root of B. Okay, what can we use with all that information? Well, let's try to prove something else. Let's try to prove, how about that something like this. The nth root of A over B is equal to the nth root of A over the nth root of B. And maybe you're starting to see that all these proofs are kind of showing that all these radicals behave in the exact same way as exponents do. In fact, in our last proof, exponents really played a heavy role in how we solved our proof. Anyway, we're going to use a similar logic to what we did last time. We know that if we were to raise the nth root of A over B, if we were to raise that to the nth power, what would we get? Simply A over B. We know this is true by our definition of roots. So what do we want to prove? We want to prove, or want to show, that the same thing is true of the nth root of A over the nth root of B raised to the n. We want to show that that is also equal to A over B. Well, how can we show that? It's actually kind of simple. And again, why are we showing that? Because if these two things, if this is equal to this, they're both equal to AB, then they must also be equal to each other. So how can I show that that's true? And let's use a different color, red. Well, again, your exponent rules should tell you that, or you should remember from your exponent rules, if you have a fraction and then on the outside of the parentheses that have the fraction in it, you have an exponent, you distribute the exponent to each part of the fraction. So you would distribute the n exponent to the nth root of A, and you would distribute it also to the nth root of B. So this would become the nth root of A raised to the n, and on the bottom you would have the nth root of B raised to the n as well. And well, we know that if you have an nth root raised to the nth power, it just cancels itself out and you get A over B. And so since this has been shown to be equal to that, then we know our proof is true, that the nth root of a over the nth root of b is equal to the nth root of a over b. Again, this is starting to look a lot like all the exponent rules we all hopefully learned in Algebra 1. So, things we know that we know two things now. We know that the nth root of AB is equal to the nth root of A times the nth root of B. And we also know that the nth root of A over B is equal to the nth root of A over the nth root of B. Those are the two things that we have proven so far. Can we show anything else? Sure we can. Let's now prove something a little kind of interesting. Let's say we have the nth root of a to the m power. Well, what does this tell us? This is the same thing as the nth root of a times a times a times a times and so on until you get to that last times a, and you've done that for m times. Again, a to the mth power just means multiply a times a times a times a m times. Follows from a definition, right? If you have 2 to the third, what does that tell you? You're multiplying 2 times 2 times 2. You're multiplying 2 3 times with itself. Same thing. A to the m is a times a times a times a m times. Well, what do we know that that's equal to? Well, you can use what we proved over here. We know this right here is true. If that's true, then we also know that this is the same thing as the nth root of a times the nth root of a times the nth root of a times and so on until you get to that last nth root of a, and you've done that for m times. Hopefully this makes sense. It's just a consequence of that first proof that we did. And if that is true, well then we also know that, well, this can be written the same thing as this way. Nth root of a to the m power, right? That's purely the definition of an exponent. We were multiplying the nth root of a m times, so that's the same thing as n power of a raised to the m power. So we have shown that the nth root of a to the mth power is equal to the nth root of a raised to the m power. It's a little confusing, but it's a lot clearer when you just see that difference. We now know that that's true. So that tells us if I have something like, let's say, I don't know, the fourth root of 10 to the third, well, that must be the same thing as the fourth root of 10 raised to the third. That is the consequence of this proof. This proof just gave us this consequence. Again, maybe you're starting to see some sort of pattern with all this exponent stuff. All right. Now let's go back, clear our page again, zoom in. And we'll try, well, first we'll list everything we know again. So we know, what do we know? We know that the nth root of AB is equal to the nth root of A times the nth root of B. We know that the nth root of A over B is equal to the nth root of A over the nth root of B. And finally, we know that the nth root of A raised to the m power is equal to the nth root of A all raised to the mth power. That's all the facts we know so far. Let's try to see if we can prove some other things. So, how about we take something like this? How about instead of the nth root, we say this is going to be the m times nth root of A. The m times the nth root of A. Well, how about we prove, let me write it up here, prove that this is equal to the mth root of the nth root of A. Well, how can we prove that? Well, we can prove that by definition. By definition, this, if we took this and raised it to the mth power, so that would look like this. The mnth root of A raised to the power of mn. What does that have to be? Well, any power, any root raised to the same power is just cancels out and you get A. So what we have to show, we're going to show that the same is true for what is on the other side of the equation. We're going to show that if we take the mth root of the nth root of A and raise that to the mn power, we're going to get that that's equal to A. Hopefully the logic's a little clear, and I'm probably not giving the greatest explanation, but hopefully it'll make a little bit more sense when we actually get to it. So, let's get started. Let's take, well, first of all, I'm going to use one of the tricks we used on the first proof. I'm going to say that x is equal to the nth root of A. So I'm going to substitute x in with the nth root of A. So instead we're going to get that we're just going to simply have the mth root of x. And now let's take that and raise it to the power of mn, or m times n. Well, what does that get us? Hopefully we remember our exponent rules, but one of our exponent rules is that if we have a power times another power, we can also write it like this. The mth root of A raised to the m power, all that raised to the nth power. Again, this follows from exponent rules in Algebra 1. Well, now let's take a look at what we have on the inside. On the inside, we have the mth power of A raised to the mth power. Well, what does that get us? Oh, whoops, I forgot something, right? Nah, did I? Nah, we should be fine. Anyway. Well, this is just going to get us... Oh, I know what I missed. Here we go. I'm not supposed to have... Whoops. It's supposed to be mth root of x. There we go. That's why I messed up. Okay. Sorry about that. Anyway, so if you notice on the inside, you have the mth root of x raised to the mth power. Well, what does that get you? That gets you just x raised to the nth power. Again, because if we're raising a root to the same power as the degree of the root, it cancels out and you just get the x. And what is x equal to? Well, we replace the x back with the nth root of a. So the nth root of a raised to the nth power, and you hopefully see what that gets us. A. And that really completes our proof, because we have taken this, just replaced the term I underlined in red with x, so brought this term over here, and we did and show that if this simple substitution with x, you go through all the steps and you get that it's all equal to a. So we have shown that this is equal to this, because they are both, when they're both raised to the same power of mn, they're both equal to a. That was a little bit of a sloppy proof, and that was just because of my delivery. Hopefully, again, you see the logic behind it, but that is that proof. Okay. Well, what can we do now? Is there anything left for us to do? Yeah, a little bit. Lastly, is this last proof? Nah, this is going to be our second last proof. All right. We are now going to show, well, this is a basic, this is barely a proof, but anyway. We have the mnth root of a to the nth power. Well, what does that equal? Well, that we know is equal to the mth root of the nth root of a to the n, which is just equal to the mth root of a. Very, very simple proof. Well, how can we apply something like that? I don't know. Let's take, let's say we have the root 3 times 2 of 4. Well, that's equal to the 3 times 2th root of 2 squared, which is equal to the 3rd root of the 2nd root of 2 squared, which is equal to the 3rd root of 2. Easy peasy. And if you're having a hard time seeing that, that just comes from the one proof we did where we showed that if you have something like this, it's also equal to the 2nd root of 2 squared. So that's just a simple little baby proof. And we have another baby proof left over. Let's say we have n, the nth root of a to the n times b. Well, what's that equal to? We know that that is equal to the nth root of a to the n times the nth root of b. And what's that equal to? That's equal to, well, the nth root of a raised to the n times the nth root of b, which is just equal to a times the nth root of b. Simple proof, but this is the thing that is probably the most important proof when we're simplifying radicals. Why is that? Well, that's the basic gist of simplifying radicals. Let's say you have the square root of 18. Well, the square root we know is degree 2. If we break 18 down, what's 18? That's the same thing as 2 times 9. Again, degree 2. And we know that 2 times 9 is the same thing as 2 times 3 squared, right? This is what allows us to take this 3 squared, move it on the outside, and get 3 times the square root of 2. The basic fundamental reason why we can simplify radicals all comes from this proof right, there. So it can be very hard to remember all these little proofs and stuff and all these different all the proofs we did, all the properties and all that. That's why mathematicians came up with the basic idea that the nth root of a is equal to a raised to the 1/nth power. This is why they came up with this whole rule, because it's much easier to think of radicals and roots just as a type of exponent, because all the proofs involve just tricking around and manipulating exponents and stuff. It's better just to think of radicals as exponents. So they defined it like this. So if you have 4, the square root of 4, that's the same thing as 4 raised to the 1/2 power. That's also why something like if we were to have, square root of 4 raised to the raised to the power of 2. Well, that's simple exponent rules. Just convert your radical into a fraction. And your exponent rules, well, if there's an exponent outside the parentheses, it's multiplied by the one on the inside. 2 times 1/2 gets you 1. So this is the same thing as 4 to the first power, which is equal to 4. I think this is easier to remember than writing it out, the other way. Well, what else can we do with this knowledge? Well, we also get some kind of weird stuff, like if you had the cube root, let's say, of 5 raised to the 2. What's that equal to? Well, that is equal to 5 raised to the 1/3 power raised to the 2. Again, you're multiplying the exponents on the outside with the one on the inside. Well, 1/3 times 2 is the same thing as 2/3. So this over here is the same thing as 2 to the 3rd power. A little weird, but again, and we also know that this is equal to the 3rd root of 5 squared. So that would also be equal to 5 to the power of 2/3. A little weird, but the easiest way to understand is the numerator of your fraction is the, quote, regular exponent. And the denominator of your fraction is the radical. You could say the degree of the radical. So one last thing, and that'll be the end of the video. What if we had, x to the 5/25 power? Well, that would be the same thing as the 25th root of x raised to the 5th power. Or you could actually simplify this fraction to 1 over 5 and realize that this is also equal to simply the 5th root of x. A lot to go through. Again, if you're in my class, do not need this for the test. This is just if you really, really, really care about math and want to understand how all of this works.